Hello everyone, my name is Ying Wu. I am a postgraduate from China Wenzhou University. Today I would like to share with you some of my research progress on directed quick search guided evolutionary algorithm for large-scale multi-objective optimization problems. My presentation is structured in the following way. First, I will begin with motivation and introduction. Then, I will move on to methodology. After that, I will introduce the experimental results. And finally, I will show the conclusion. First, I would like to tell you the motivation and introduction of this paper. We observed that in real-world applications, there exist numerous scenarios involving multi-objective problems, such as portfolio optimization and mesostructure optimization. When the number of decision variables in a problem exceeds 100, it becomes a large-scale multi-objective optimization problem. For instance, in machine learning, when optimizing the parameters of a neural network with multiple hidden layers, the number of parameters can increase to thousands. This is a typical large-scale problem. Nevertheless, as the dimensionality of the decision space continues to grow, the performance of traditional multi-objective evolutionary algorithms deteriorates exponentially. A phenomenon commonly referred to as the dimension disaster. Hence, it becomes imperative to explore dedicated algorithms designed to tackle large-scale multi-objective optimization problems. In recent years, large-scale multi-objective evolutionary algorithms, here we call LSMOEAS, have attracted a lot of attention from scholars at home and abroad. In general, these algorithms can be classified into two categories, according to whether they directly explore the original search space or not, namely the search space reduction-based LSMOEAS and novel search strategy-based LSMOEAS. These algorithms have good performance, but there are still some open issues. For the first class, while they possess the capability to accelerate the convergence using limited resources, they only explore the local spaces, which makes them easy to fall into local optima and degrades the population diversity. For the later class of algorithms, it has been demonstrated their search capabilities have been greatly improved. However, they still suffer from a slow rate of convergence due to the cost of expensive computation. Based on the above observations, we can easily conclude that it is vital for LSMOEAS to possess efficient search capabilities in the high-dimensional decision space, producing high-quality offspring. Motivated by the above, we combine the ideals of dimension reduction and novel search strategy to propose a novel directed quick search guided large-scale multi-objective evolutionary algorithms called QSLMOA. The contribution of the algorithm is mainly in the following two parts. First, we propose a sampling strategy that identifies promising sampling directions in a large-scale decision space to reduce the dimension of the problem and accelerate the convergence. Furthermore, we introduce a quick search-based strategy for generating offspring, which leverages sampled solutions to facilitate efficient exploration in the decision space. This approach significantly improves the search capabilities of the algorithm and enhance the convergence rate of the population. We will then describe these two strategies in detail. For our proposed sampling strategy, it is crucial to identify promising sampling directions in the original large-scale search space. Therefore, we first need to obtain direction solutions, which are used to construct the sampling directions. Here, we define the direction solution in this way. A solution X is a direction solution if it is the closest one to the ideal point. To enhance the diversity, We need to further divide the whole population into multiple subpopulations and select their respective direction solutions in each subpopulation. Therefore, we use a set of reference vectors to construct subpopulations. Specifically, we assign each of them to the nearest reference vector according to their respective objective values. Next, we use these direction solutions to construct the sampling directions. For each direction solution xk, we construct two different directions in the decision space for it. Specifically, one direction points from the highest point in the decision space to itself. The other direction is formed by connecting two randomly selected points in the decision space. Note that the motivation for this design is to guide the search towards a Pareto set, as well as enhance the diversity of the population. In essence, through the above operation, the original large-scale MOP has been transformed into a small-dimension MOP. In other words, our task now becomes to sample high-quality points in these defined directions. Here, we choose to use the uniform random sampling strategy. Specifically, we randomly sample ND solutions uniformly in each direction. Notably, the reason behind adopting random sampling is that random selection allows for a higher diversity of the obtained solutions, making the population less easily fall into a local optimum. In this way, we efficiently screen out a batch of more promising individuals from the original large-scale decision space to accelerate the convergence of the population with maintaining the diversity. After sampling, we obtain a set of promising solutions in the original large-scale decision space and hope to guide the evolution of the population with these solutions. Nevertheless, despite our efforts to enhance diversity and randomness in the sampled solutions, it is important to acknowledge that the directed sampling in reduced space may limit the availability of global information. Consequently, the search process may fall into local optima. In view of the above, a new reproduction strategy is proposed to improve the search capability of the algorithm. First, we need to introduce one of the most important mechanisms of this strategy, which is called quick search. So, what is the quick search? In simple terms, it is to use a set of high-quality solutions in the population to get the direction of the search and thus accelerate the convergence of the population. Specifically, we distinguish elite solutions from inferior solutions in the population based on some strategies, then allow the inferior solutions to explore the search space in the direction indicated by the elite ones, ultimately enhancing the quality of offspring. Therefore, first, we need to combine the current population and sampled solutions, then divide the population into several subpopulations, which is the preparation for calculating APD later. After calculating the APD of each individual, the individuals in each subpopulation were arranged in ascending order. Here, the top quarter of the individuals are assigned to the elite solution set SE, and the rest are assigned to the inferior solution set SI. Finally, our quick search mechanism is used to generate offspring and perform polynomial mutation on these solutions. In this way, we have successfully guided the population towards a favorable direction through a specific search strategy, obtaining high quality offspring and accelerating the convergence of the population. To verify the effectiveness of QSDRS, we compared it with its variant, denoted as QSLMOA-PM. The difference between these two algorithms is only that the former uses polynomial mutation to reproduce offspring, while our algorithm adopts the quick search to do that. This table lists the average IGD results of these two algorithms answering objective LSMOP problems. It is clear that quick search works better or comparably in all test instances, which validates this mechanism is more effective than the conventional reproduction strategy. Next, to verify the overall performance of the proposed algorithm, we compared our algorithm with 6 state-of-the-art LSMOEAS on LSMOP problems with 2 and 3 objectives, while the dimension of the decision variables range from 500 to 5,000 respectively. Due to space limitations, I do not show the relevant IGD results here, but our algorithm does have an excellent performance in dealing with LSMOPS among all the compared algorithms. We also plot the Pareto fronts obtained by our algorithm and 3 LSMOEAS with different types, and compare them with the real Pareto fronts for corresponding problems. This is the result of 2 objectives. It's about 3 objectives. It is clear to see that compared to these LSMOEAS, solutions obtained by our algorithms can cover and get close to the Pareto fronts better, which indicates our algorithm performs excellently in the distribution and diversity of the population. Finally, I will make a small summary of this presentation. The main idea of this algorithm is to reduce the search space by identifying promising sampling directions in the decision space and obtaining a set of high-quality sampled solutions. Subsequently, with the aid of the sampled solutions, further exploration is conducted in the decision space to generate offspring solutions, guiding the population towards a more convergent direction. The performance of our algorithm has been improved by the comprehensive comparison experiments with the 6 state-of-the-art LSMOEAS. The result illustrates that our algorithm has an excellent performance in convergence and distribution. However, from the experimental results, it also can be found that the performance of our algorithm in solving some test problems with mixed modality needs to be enhanced. The reason behind this fact may be that the accuracy of the sampling critically depends on the selection of the direction solutions. Therefore, in the future, we will strive to develop an effective strategy to adapt to more complex problems. Okay, this ends my presentation. Thank you for your attention.